All right, good morning, everyone. Now, today we're going to be talking about how AI works. So far, we've been talking about text pre-processing, where we essentially went through the process of flattening our string, getting it to a bunch of ones and zeros. Today, we're going to be diving into the concept of deep learning, which is essentially teaching the machine how to learn. All right, we're going to see how our machine learns depending on our different connections that we may have inside of a neural network. And we're actually going to give our machine a mission. All right. Now, with that said, we're going to talk about the steps conceptually first. Once we talk about the steps conceptually, we'll be diving into how to prepare our data. So, this whole part one of our lectures can be regarding data pre-processing, where our start state will be where we have just a ridiculous amount of data. We're going to flatten it, we're going to standardize it, scale it, and make sure that it's ready to actually start training a model. All right, let's start off by talking about what a model may look like and how it works. Okay, maybe, not maybe, of course. Something is going wrong because why wouldn't it be? Yep. All right, we're not going to dive too much time into that. Okay, perfect. So here we can see a neural network on the left-hand side. And actually, I'm going to go ahead and take the time to draw it out. Now, when I described to us deep learning before, I told you that it was essentially a funnel, right? A funnel that takes in a ridiculous amount of information that we may see being provided to us in different formats. That funnel was supposed to take said data, make connections between said data to understand which one of these has the most meaning or what should actually they should actually consider when making a calculation. And at the very end, although it is learning, our machine is actually just making an educated guess, right? At the very end, our machine is deciding, okay, well, did taking into consideration what I was just given and everything that came out from this funnel, I have to choose between one, two, three, or four. Right? Well, how can I do that? How can I actually understand? How could I actually decide which one of these numbers is provided to me? Well, once it takes all of these into consideration, so let's say this comes out, and from that data says, hey, I'm pretty sure that your guess should be number one. This one goes through and it states, hey, I'm pretty sure that your guess should actually be a two. A different data set goes through, populates on the other side. I'm pretty sure your guess should also be a two. And another one populates. This one says, hey, this should be a four. And we get a final one stating that this should be a two. Right? Well, out of all those data sets, two appeared the most. So percentage wise, two would be my decision that makes the most sense. So my machine would make the educated guess of saying, hey, I honestly, I can't understand what you're telling me, but if I'm going by the probability, probably the correct answer to this is the number two. Let's think about this from a different perspective about this funnel. Oh, there you go. Let's say that rather than receiving just a bunch of data, what we receive is an actual picture. All right, we get a picture. Oh, let me do that. This picture has some straight edges. Let's give it some background as well. And this picture holds the number 3 inside of it. All right, well, this is the picture that I'm being received or that I am to receive. And now I want my machine learning algorithm to essentially determine, hey, depending on this picture, what is the value that this picture is holding out of these numbers? All right. Well, there's the possibility of receiving pure data, and we know that our machine learning algorithms will only learn from ones and zeros. So there needs to be a way to translate this picture into a bunch of ones and zeros. Can anybody think of a way to do that? At this point, we're done with our front end module, so we should know a little bit about what pictures look like when the web is looking at it. Think about it from a colors perspective. Is there a way to grab colors as ones and zeros? All right, let's go ahead and take a look here. I'm gonna go ahead and actually turn this into a different shade. I would like to inspect
Are
this.
you just talking about when like you use the different numbers that are associated with the color and like tailwinds?
Nice. Yeah, so there's one way of doing it, right? We're talking about the RGBA combination that makes a
Yeah.
color.
All right, cool.
Nice. Yeah. So if I'm taking a look at the RGBA combination, well, that is going to get broken up where we're taking a look at independent pixels. Oh, let me bring that out a little bit. So that is going to get broken up into independent pixels. Those pixels will hold the numerical value that matches the image that we're working with on the right-hand side, where maybe each one of these pixels sold something like 0 point, etc. I'm not going to go through the process of drawing it out because judging by the way TL Draw is treating me right now, it is not going to look very pretty. Let's see, let's try it out. Let's say that this is 0.21. This one is a combination of 1.2 and so on. All right, well, all of these would eventually get flattened into a two-dimensional array, which it pretty much already is, right? Where in this two-dimensional array, we have an entire array that's supposed to represent the picture, and then we have a array for each row of pixels that are within the image. Now, all of this data gets fed through the machine learning model. The machine learning model takes a look at each one of these list items that are being passed in and says, okay, well, judging by which one of these are actually colored in or hold the number or a darker value inside of it that would represent a border between white space and the image itself, I'm going to guess that the output here is the number 3. Right? And that's essentially how machine learning works. It's just making an educated guess from the data that we are providing it. All right. So does anyone have any questions up to this point? Okay, great. With that said, let's go ahead and start talking about our neural network and what a neural network looks like. This funnel here is actually quite a bit complex. When we're taking a look at this funnel, what this funnel is actually representing is something called a neural network. Let me go ahead and stretch it out a bit. This is essentially a human's attempt to try to teach a machine to mimic the connections that we have ourselves, right? We're essentially creating a tiny brain that can think or that can mimic thinking and come up with a solution. And it works in a couple of different ways. So one, we have our input layer. And this is where we'll be providing our user input, which may be a bunch of ones and zeros. Um, Let me go ahead and map this out. Nice. All right, so these are actually our features that we will be passing into our model. At the very first layer, we are going to have something called an input layer. This is where features are accepted. Now, this one doesn't become very complicated, right? Because our input layer is essentially taking a one-for-one match for the number of features that we're providing it. But what's really cool about our input layers or linear layers as we continue moving forward is that they don't just provide to us or they don't just stop by receiving input. They also create an output of neurons, where this output of neurons may either trickle down or open back up. All right, let's say we trickle it down to 3. From there, what we would have is a linear layer, which is not going to look very different from the input layer. It's actually just going to be identified as a linear layer. As we said before, this one would have 3. All right, there's a one-for-one pass between the layer prior to it and the next layer, where now we would receive 2 neurons being outputted. And then finally, we would have something called an activation layer, where the activation layer is making sure that the output is something reasonable to what we're looking for. So if what I'm looking for is a binary classification of true or false, only 1 neuron should be provided. All right, so now this is happening. We're trickling down the effect. From there, activation layer outputs 1 neuron, and this 1 neuron comes out of the learning model. Once that 1 neuron comes out of the learning model or the neural network, we can make a decision, right? So let's say we have our decision tree or possibilities, and our possibilities are pretty simple. It's either true or false. So here's true, and here is false. Well, from this 1 neuron, we can create our question of, hey, is this value that the neural network outputted true or false? And this is typically determined by how heavy this neuron is. So if it's anything above 2.5, it comes out to true. And if it's anything but, oh, excuse me, if it's anything above zero point 0.5, it comes out to true. And if it's anything below zero point 0.5, it comes out to false. Right? So we're looking at something that is evaluated by zero point 0.5. All right. Well, now these are the separate layers, and that's how information will eventually trickle down to a decided possibility. We haven't gone into how these input layers actually work and how they're able to generate an output at each independent layer. So before we go into that, does anyone have any questions over this neural network and how it essentially just trickles down depending on the features that it receives? Okay, awesome. Doesn't seem like we have any questions. And I do want to say that this is essentially the same thing that happens with language, right? We pass in a specific word. That word holds a bunch of different neurons inside of it. And from there, our neural network would decide, well, hey, which word is it that we're looking at in our possibilities, right? And this is how it would be able to understand language. Rather than understanding language, we are now jumping into the language processing portion, where it's actually where the machine would actually be processing the language that we passed in. It's no longer understanding. That was our pipeline that we built over the last couple of days. Now it's actually processing text to be able to start generating an answer. All right. Now, as I said before, each linear layer or each layer within our neural network is supposed to receive a one-for-one input from the previous layer and then output a filtered down function. How does this happen? Right? How if I do an input where I'm receiving 4 neurons and I tell it to output a total of 3 neurons, how does it know to trickle down to 3? Well, it does this through math. And it's essentially going to conduct something with weights and biases, where each neuron, let's go ahead and color this red, is actually going to affect every single neuron on the output layer. Let's make this one gold. Let's make this one blue. I apologize to everyone for taking some time drawing this information. And then finally, let's make this one green. All right, so you can see it's already starting to look a little clustery. This input layer has quite a bit of calculations built into it. When it's attempting to create the very first neuron here, it's going to take into consideration neuron 4. It's going to say, okay, well, how important is neuron 4? This is called a weight, right? So how important is neuron 4? And it's going to continue doing that for the remainder of the text. It's going to say, okay, well, let's say neuron 4 takes number one priority. This neuron 2 is actually third in priority wise. Neuron 5 or neuron 3 is second in priority wise, and neuron 4 is actually fourth in priority. So that's important, how important they are. Okay, so it starts running that calculation and it's attempting to generate our very first neuron on the output layer. After it takes into consideration all of the different weights or calculating how important each neuron it is, It says, wait, do we have any biases? Meaning, am I favoring a neuron way too much in comparison to the others? Right? If we were to add a level of complexity to this, let's say that this was five, right? Well, at this one, we're saying, hey, neuron, the very first neuron is the highest priority. It carries the most amount of weight. Three is next in the line. Then we have four next in line. And then finally five. Well, is there a bias here? Is there any one neuron that's being taken into consideration a lot more than all of the other neurons? Okay, Jake, I see you shaking your head yes. Which neuron would that be?
It'd be the red one.
Nice, yeah. So our red neuron here, the very first one that's being passed in, is the one that's being taken into consideration way too much. Right? So our biases say, okay, well, we do have a bias. Okay, so what do? We're going to flatten this bias prior to creating the next neuron. So by flattening it, they take this bias and they say, okay, well, look, everything else is at three, four, and five. You're at one. I get that you're supposed to be important, but I can't have you being so important that everything else is going to get thrown off. So I'm going to turn you into a 2.5 instead, right? And it mutates the essentially how important this neuron is when it's being taken into consideration. And then it starts grading. Okay, well, from this calculations, I can say that this neuron 3 is going to hold the value of, let's say, 1.2. This one will hold the value of 2.2. And this one will hold the value of 1.5. All right. And that gets passed as a one for one to the next linear layer. Then the priorities happen again. Okay, well, which one of these is the most important? Well, this holds the heaviest value, so maybe this is the most important one. All right, we say, okay, well, this one holds priority over all of them. This one is a 1.5. That's an easy two. Now we have a three, and it repeats the process. It says, hey, which one is the most important? This neuron is the most important. Fantastic. So whenever we run our calculations, we'll base it from this neuron here. All right. Well, do we have any biases? No, I don't think we have any biases in this state. Okay, perfect. Then let's run our calculations where our second neuron takes the most importance and starts outputting some values. All right, well, now our neurons may look something like 1.8. And then we may take a look at something like 1.9. Oh, not too. And it trickles down. This gets passed down onto the next neural layer. This is now our activation layer. And we'll go into the math of activation layer later on. But again, this is going to take these neurons, determine which one is the most important. This may be priority two. This may be priority one. State, well, depending on these two outputs, let's see what we can output here. Well, what I've came up with is a 0.75. All right. Then it makes my decision. That 0.75 becomes my output layer. It is greater than 5, so my neural network evaluates to true. All right. And that's happening at every single layer of the neural network. And essentially, that's how we come up with an answer here. We have weights and biases happening at each independent neuron that interact with the mathematical function and each linear layer. And we'll see that here shortly. I'm not going to explain the math because one, if I'm being completely honest, I wouldn't be able to. And two, it is some very complex stuff. All right. Does anyone have any questions over how a neural network is essentially taking in something called features and then outputting a target or label? which is essentially the answer. It's best guess.
I'm guessing that like because this is like all the concepts associated with neural network for what we're learning. I guess the tools that we're using essentially are creating this neural network. Essentially, that's what we're going to talk. Is that what PyTorch is primarily looking for?
Yeah, so PyTorch is actually going to create our neural network for us. Yes, that's correct.
Oh,
All right. Awesome. Okay, great. Well, now that we understand what this funnel looks like, we understand the data that we're about to bring in. We've done this with text, right? Where we say, hey, how are you doing? It goes into a text pre-processing pipeline, and eventually it outputs a array of arrays where we may have zeros, 1, 2, 0, 0, utilizing one of the processes of vectorization that we learned yesterday. All right, so we know that it happens with text. We have an example of how it happens with images, but there's also the pattern of statistics. So let's talk about the problem we're going to be solving today. All right, so today we're going to be going into the student performance data set. The student performance data set is a data set that provides to us the different attributes regarding a student. So it's going to give us a student ID. It'll give us some demographic details as to what the student may be going through. We have age, gender, ethnicity, parental education, study habits. There's parental involvement, extracurricular activities. All of it is being provided to us. And this is what we're trying to find out, right? This is data that's already collected, meaning these are students that have happened in the past, and there was some sort of study, and they've collected this data, and they discovered these patterns. Well, now what we want to do is we want to take a neural network, right, that will learn from this data set that we have here, which you can view it. It's a pretty massive data set, and this is actually not all of its columns. If you scroll up to the top, it's telling you it's only showing you 10 columns out of 15. If you do all 15 columns, you can see there's quite a bit of input here, right? All right. So we're going to take this data set. We're going to train our neural network to guess, hey, if a student currently enrolled in this school holds these demographics, what is the likelihood or what GPA are they likely going to achieve? Right? That's what we're going to train our neural network to do. But before we do that, we have to prepare our data to be fed through our neural network and train it. Does anyone have any questions about that? Fantastic. Then let's get on to it. It is time to prepare our data. Okay, so we talked about what it is that a neural network is, how data applies into it, and how it's actually going to be able to learn. So the start state here is we have some data that may be unbalanced. It may be dirty, may have some null values, include features and targets. The end state that we want to reach at the very end of our data pre-processing pipeline is we want to have a clean training data and testing data, where each set holds a set of features along with their matching target. All right. Well, something very important here. We want to divide this entire CSV file, and I'm showing you in Kaggle, but I already have this file. In case you're following along, this link to this CSV file or this data in Kaggle is inside of our curriculum. So you could just open that up and grab that data yourself. But inside of data, oh, I don't have it. Let's go ahead and grab it real quick. Gonna go ahead and download my data. I believe it comes in as a zip file. Okay, let's open that up. And once you open up that data, you're going to see a CSV file populate. There you go. All right. So here's all of this data that we saw in that nice, neat table being represented. inside of VS Code as a CSV file. And I'm actually going to rename it because I don't like the name of it. So I'm going to change directory into data. I'm going to move student CSV file into student data.csv, just so it's a little bit easier to read. All right. I believe I also have, oh, I don't have it. Okay. There is an Excel extension that you can install. I don't want to occupy class time to go into that, so I'm just going to quickly mention it. And if you're interested, please look into it. It's going to format your data so that it looks like an Excel sheet. All right. Now, here's all the data that I'm receiving. And sometimes I may have some null values. This data set's actually pretty clean, so maybe I won't have to account for it. But if I'm having to look for null values in the entire data stream as it's coming in, this could take me hours, right? And also, humans are not really reliable for something like this. If you're just staring at a sheet with a bunch of numbers for a pretty long amount of time, you're bound to miss something. So instead, we're going to do this programmatically. We're going to ask our Python to clean up our CSV file. All right, well, first of all, we have to actually read our Python, or excuse me, we have to actually read our CSV file. Now, what we've learned in the past is we can actually do something like import CSV, and after we import CSV, we can say, hey, with open, I can declare that what I want to open is data slash student data.csv as v, and you can see that it pretty much provides me the entire reader there, right? That's what we've learned up to this point. And this isn't necessarily wrong, right? It would work and it would be able to provide us a list of data. But now that we're starting to work with data science, because at this point we are quite literally in the data science community, right? We are taking a look um, at data being collected. We want to be able to read it efficiently, and we want to be able to manipulate it efficiently. Although Python is a fantastic tool for being able to do this, there are other tools that are attached to Python that we can utilize to do an even better job at manipulating data. And in this case, we're talking about pandas. So we're going to import pandas as PD, and I'm going to grab my data by stating PD dot read CSV. When I read the CSV file, I'm going to tell it that I will find it within the data directory named student data.csv. And let's go ahead and take a look at data. Gonna execute this. This is probably gonna take a while. Oh, there you go. And there is all of my student data now being able to populate. Let me give us a little bit more real estate here. It tells me that we have a total of 2,392 rows of collected data samples, and there's a total of 15 columns. Nice. We're able to grab our features, and we're able to grab our labels. Features, meaning all of the information that would come up to a conclusion, and a label, meaning what we actually want to achieve, right? Which is our grade class here. That is our label. It is our target. All right. So we read the CSV file. We now have data available to us. We did this utilizing pandas. Well, now I kind of want to balance it out a little bit. There's some interesting things that we can do with data. For example, we can take a look at data and we can specify a header. So let's say all I wanted to do was take a look at grade class. When I execute this, only the column of grade class will be returned. If I wanted to take a look at a row, we could do data.iloc, and then we could specify the row number. So let's say we want to look at row 1. Then it would show me just row 1. And if I wanted to take a look at a variety of data, So let's say from row 1 to row 3, then it would show me from row 1 to row 3. It is essentially slicing the data frame so that I could view only the data that I want to see. So really nice, powerful features that are coming in from data frame. If you had to do this with a straight Pythonic language, it would take quite a while. There would be a lot of considerations that you have to do, and you would have to do, there's a lot of safety features that you would have to account for in order for your dictionary loading to work correctly. All right. We're now handling missing values. If there are missing values in our data set, that could possibly throw off our entire data, especially when we're teaching our machine learning algorithm how to learn. So how could we account for missing values?
Is there a way for within the Panda program to sort through, like you said, missing values or how we define null in there?
Okay, yeah, maybe I just want to see, hey, is there even missing values anywhere being seen? Let's do that. Let's do data dot is null dot sum, right? And that will actually give me the sum of all null instances. So in this case, every single one of my columns do have a value inside of it. So there's nowhere where my data may have none. Okay. Well, I have a question for you all, right? And you guys could explain it to me if you were just the person conducting this experiment, right? Let's say you're conducting some experiments, you'll have some numerical values that you're working with, and all of a sudden you figure out that one of is missing. We can't have that. We can't have in this missing value. We can't just leave it blank. How would you fill in that slot?
Just thinking, um, you could either input some sort of value that is like going to stick out so that you look at it and like, oh, there's no way that's true. Or you could take some sort of average or predictive value based on the other values given.
Nice. That is awesome. Thank you so much, Jake. So both of those options are completely valid, right? We could come up with something default. Just say, hey, if there's any sort of default anywhere, or excuse me, if there's any sort of null anywhere, I'm just gonna give it the value of one. In the case that that is not something that we want, and although it works, it's not necessarily going to be the best answer. You would want to fill it in with not the average, but the mean of every single row, right? So let's say that we have all of our different ethnicities and they all have their own score. Well, on we don't want to just fill it in with the average, right? Because the average may not match one of those different ethnicity values that we have. We want to fill it in with the mean, the one that's most common upon all of them. That way we can make sure that we are accounting for data correctly. Right? Now, I'm going to demonstrate this. You're really not going to see a change, but you do that by running data dot fill. These stands for null, right? So for any blank cells, I want to fill them with data dot mean. So I want to fill them with the mean placement of said column, and I want to do it in place. So I would say true. Again, unfortunately, you wouldn't see necessarily any difference if I go ahead and add a print statement here and add a print statement here, both of them would just show up as zero, right? Nothing would change in this case. But very important for all of us to know, in case we're dealing with data that does hold blank values, which is very common, unfortunately. All right. Now, with that said, there is going to be a lot of edge cases that you should account for with data. This data set was specifically chosen so that we don't have to deal with too many of those edge cases. So if you are interested in learning about data pre-processing pipelines, I strongly recommend getting familiarized with different data sets and going through the process of actually analyzing the data, creating heat maps, relationship maps. Those are very important for understanding which features are important and which ones are not. All right. So now we handled our missing values. Now that we've handled our missing values, we have to scale and standardize our data. Well, what does that mean? This makes more sense if we're looking at a visual representation. And I am so glad that they're giving us this, right? So here we have a chart. And this chart has an upper and lower limit. I'm not saying this is necessarily the one-for-one representation of what we're working with. But in the case that we're working with our data, and as we're training our data, we'll realize that one of our inputs is outside of that upper limit. Well, that would create a very significant spike that would happen out of nowhere in our chart here. Right? We could have multiples where again they could happen out of nowhere after a small decline. And this could create some problems whenever we're training data. What problems could it create? Can anybody take a guess here?
And it would skew the average or
Yeah, nice. Awesome, Jake. It would actually skew our data. It would skew our learning models' ability to understand the data that we're presenting to it, right? We need to make sure that our data is standardized and that it always falls within our left and right lateral limits. I say lateral limits a lot. So the way that I think about it is I used to be a mortarman. So whenever we established a firing range, we would have to establish our left and right lateral limits whenever we're shooting mortars. Those are kind of like a safety feature, right? It's the same thing here. We're about to train a learning model. So we have an upper and lower lateral limit. And we want to make sure that all of our data stays within that upper and lower boundary. Now, we can't do this without being careful about not skewing our other values, right? Because if I bring in an input that fell on the out-hand side, well, I still want it to be significant, right? I still want it to be recognized. But I can't just put it at the very top of the parabola because now its significance is different, right? It's not being taken into consideration here. So I have to conduct quite a bit of math to not only standardize the values that are on the outside, but also standardize the values that are on the inside so that anything that fell outside of my left and right lateral limit can still hold a significant impact when my learning model is attempting to learn connections. Now, with that said, there's quite a bit of math that goes into it. Instead of utilizing all that math or trying to learn all that math from scratch, somebody has already created this tool for us from sklearn or within sklearn. So we can state from sklearn dot preprocessing, I want to import standard scalar. Now, standard scalar is good for scaling and standardizing data. We can start doing this to our entire class. And let's take a look at our application here. Let's go ahead and say scalar is equal to standard scalar. We're going to make an instance of that class. And let's talk about scaled data. When I do scaled data, I'm going to do this to scalar.fit transform and pass in my data attribute. Now, before I do this, I'm going to go ahead and print data where I want to take a look at row 1. I'm going to do the same thing, but I want to take a look at scaled data. So it looks like scaled data is no longer a data frame, which is okay. We can go ahead and just do index 0 in this case. All right, so we can see the mutation happening here. right? Or 1002 has now turned into -1, etc. Our age of 18 has now turned into a 0.4, and so on. So all of our values are currently changing, and they're being taken into consideration. We are falling within that upper and lower lateral limits. But something really important that I want to highlight to all of us, the way I have my program currently set up, grade class is the target that I'm trying to achieve. When I fit it to scalar, grade class has now turned into 0.79. Is this okay? Is this something that I would like to do? Someone other than Jake this time. He's been really been leading the charge this one. I guess is okay. All right, no one is speaking up. I'll take it. So in this case, this is not something that we would like to do. All right, we don't want to change the value of our target. This should stay as its own value. Regardless of what happens to our features, our output or our target should stay the same. So let's fix that. We are going to divide our targets and labels. We need targets and we need features, or we could call them labels, but for now, I'm going to call them targets. All right, well, my features, that's easy. My features is the entire row of grade class. Excuse me, my targets are my entire row of grade class, and my features are all of my rows with the exception of grade class. So I'm going to go ahead and drop grade class. And I'm going to go ahead and make it clear that, hey, we don't want to mutate the array or the multi-dimensional array. I want to keep it the same. I just want to drop that last axis. Okay. Well, now instead, to scale data, the only thing that I'll be feeding is my features. So after I execute this, we can see everything's still happening the same. And my number of features has decreased by 1. Right? Grade class is no longer being mutated, and it's staying in as the number value of 1. Awesome. So now I have standardized and scaled features. So let me go ahead and rename that to features. And I have targets that are ready to go. But now the last portion. I want to create some training and testing data sets. Okay. Why should they be different data sets? Why not just train my entire learning model on all of the data that I've collected? I don't have that much. I only have about 2,500 rows, right? So I have to make sure that I maximize what I do have. So why not just utilize the entirety of the file? Why not all 2,500 rows going straight into my model when it's trying to learn?
I guess the idea is you want to have some type of benchmark to compare from, so you're not relying heavily on the set that you have because you won't be able to compare it, so you really have a bias associated with your test.
Okay, nice. Yeah, awesome. So we want to make sure that the test is coming in, maybe at 20%. And the standard here would be like an 80 to 20%, right? So 80% of the data will be turned into training, where 20% of the data will be turned into testing. Okay, great. That is awesome. Now, I also want to take the time to randomize said data. Why would I want to randomize these training and testing sets?
So that there's no bias?
Nice. So there's no bias. Awesome. I think it's very close, right? What we're looking for here is we want to make sure that we're training our model to guess correctly. I don't want to train my model to memorize correctly, right? So these are two completely different things. I wanted to train it to learn. I don't want to train it to memorize. This is called overtraining. And I like to make the comparison of I have a specific instance. I remember being, I think, in high school, and we had a test where essentially, if you failed the test, you would get the same exact class over and over again. And not only did you get the same exact class over and over again, it was a 30-minute class. You would get 10 minutes to complete a 10-question quiz over and over again. But the 10-question quiz was always exactly the same. And you could take it an unlimited amount of times. Now, I remember me as a person, at some point I said, well, screw the class. I stopped showing up to the class and I would just take the quiz again and again and again. And at the end of taking the quiz, they would show us the correct answers. They would say, hey, listen, this, I see that you chose this, but this isn't correct. The correct answer would be this. Now, at this point, I wasn't learning the material, right? I was just memorizing the correct answers. And eventually I was able to take the quiz successfully and just select all the right answers, not because I knew the problem or because I knew how to solve the problem, but because I knew what the right answers were. Machine learning algorithms can work in that same way. If we continuously present it with the same exact test, we're going to tell it, hey, this is wrong. This is wrong because of X, Y, and Z. I need you to readjust your algorithm so that it's able to make a better guess. The next time we present it with a test, we want to make sure that that test is different and that everything gets randomized at every training or testing iteration. This will make sure that the learning algorithm will actually learn and make meaningful connections rather than memorize. All right. Now, with that said, there is a tool that is built in that we can utilize to actually scale our features or destroy our features. And this is called the training test split. Let me fix that there. I'm going to say from sklearn dot model selection. I want to import train test split. Now, train test split is going to receive my scaled features as an argument. It's going to receive my targets as an argument. And then I'm going to specify to this training test split how big the test size should be and how often it should randomize. So for example, I can state, hey, the test size is 20%. In this case, that would be represented as 0.2. And the random state, so how often should you randomize, would be at every 42 rows. So after every 42 entries, randomize. So it's creating batches of 42. Go ahead and do this. So it creates batches of 42 randomized rows. And it does this with a 20% testing, and it does this with an 80% dedicated to training. All right, let's take a look at the output here. Okay, well, that's giving me an array of arrays. And it can get a little complicated to be able to read this, especially because of the output and the way that it's coming in. So let's talk about what train test split is actually going to return to us. Well, training test split is going to return to us a array where this array holds 4 separate values. It returns, I guess we should call it a list, where that list holds 4 separate values. First is going to give us our training features. It's then going to give us our testing features. It will also give us our training labels or targets and give us our testing targets as well. All right. With that said, we could just deconstruct it. We could say, hey, this is training features. We have testing features. We have training targets. And we have testing targets. When we run this, there won't be any output. But if we take a look at our training features and testing targets, and we execute this, they're going to be of the same exact length. So this is my array holding all of the features where every array is matching to their independent answer. So for example, this first row, or this first batch, I apologize, in the array should come to an output of 4. And we're going to see that later on once we're actually training our data. All right. Does anyone have any questions over what we've done to our data so far? And let me conduct a quick review. First, we grab our data. After grabbing our data, we want to make sure that there are no missing values or no blank values in there. We then divide our features and targets and scaled all of our features. After scaling our features to fall within the left and right lateral limits to make sure we're not skewing our data, we're dividing our features and targets into a testing and training set, where 20% will be dedicated to testing, and it will create batches of 42 entries where their entries will be randomized. Now, I'm not saying that every single column is getting randomized. I'm saying the order of the rows are being randomized. All right. Any questions up to this point? Fantastic. In that case, there's one last step that we need to take to make sure that our data is ready to be fed into a model and to allow our model to learn. And that's placing it inside of a tensor data set. Now, tensors are very similar to a NumPy array, but the only difference between tensors and a NumPy array is that they're compatible with PyTorch's network, right? So we're going to start utilizing PyTorch tools in the next lecture. So we want to make sure that we take this NumPy array and set it up so that it can start working with PyTorch. So I'm going to state from torch, and we want to import torch actually. Then I'll say from torch.utils.data. I want to import two things. I want to import data loader, and I want to import tensor dataset. Let's talk about these two things. Now, data loader is meant to feed data into our learning model, either at training or testing. But it feeds data sets to the model. The tensor data set is meant to be fed onto a model by a data loader, but it takes in both features, or let's say a set of features with its matching label. All right. Well, we have our features and labels from here. We have our training and testing information. So let's go ahead and grab all of that. I'm going to bring it down. What we're essentially stating is that our training labels should also be matching here. So here we'll have a tensor data set that will also be wrapped by data loaded. That's the end state that we're trying to achieve here. So if we're putting it into practical application, well, first we have to create our tensor sets. So we can create our training set, which is our tensor data set. And I just see that I misspelled that. Perfect. So we take our tensor data set that is going to take in training features and training targets. We could do the same thing down below, but instead of training, we want testing features and targets. And then finally, we have our training loader, which is going to be a data loader that takes in the training set. We're going to specify the batch size here being equal to 32. And we're going to add another state of randomness by shuffling them, making them true. We could hold the same values here, just that instead of training data loader, we want our testing data loader. And if I take a look at them now, when this populates, oh, looks like we have an error here. Module torch has no attribute CUDA. What are you talking about here? Is it from the import torch? That's fine. Okay, so training is not defined. Where is that coming from? Are you highlighting something for me?
Is it supposed to be underscore?
Comma T. Yeah, thank you so much. All right, nice. Let's try that out one more time. Okay, so now tracing set, tensor size 0 for tensor. Integer object is not callable. Okay, I'm starting to run into some issues here. Let's see. The lower feed data into our learning model. Oh, no, we already talked about that. It's happening here at target. Okay, got it. So it looks like our training target is not matching the format that we're looking for. So let's go ahead and see what we can do about that. We are at time, so I'm going to go ahead and pause the recording. And then when we reconvene at 11 o'clock, I'll quickly cover what the issue was here. I'll stop the recording and then start a new one, everyone. All right. So let's take some time to get off away from our machines. There are some assignments that you can complete. If you don't necessarily want to get your hands dirty with coding, then I would just conduct a little bit of research regarding how PyTorch works. That way we can have an intelligent conversation in this next lecture. All right, everyone, enjoy your break, and I'll see everybody back at 11. All right, welcome back, everyone. So my mistake was a simple one. Luckily, I actually skipped a step, right? I was just talking about how our data model is going to expect tensors and not NumPy arrays, and we need a way to transform them into tensors for PyTorch. And then I completely just went into data sets and data loaders without actually transforming them into tensors. So this block of code was what was missing. You can see here we can import torch, which comes from PyTorch, and we utilize torch.tensor to be able to convert those. Something that I do want to point, because our labels are whole integer numbers, as you can see here, we want to make sure that we utilize torch.long for the data type. Everything else can stay at float 32 or float 64, depending on what kind of accuracy you want. All right. Does anyone have any questions over how we standardize our data and prepped it inside of data loaders in order to be able to train our data? Okay, fantastic. It doesn't seem like we have any questions. So